Thank you. So hello everyone, good afternoon. As Evan said, I will be talking about mode coupling among gravito-inertial waves in slowly pulsating B stars, work that has been done in collaboration with a team of collaborators at Leuven, KITP, and other places. And I would like to give you a fair warning while starting this talk that I will be describing this from an observational point of view. So what I mentioned in my title is quite a bit of jargon. So I would like to start out by defining what slowly pulsating B stars actually are, and in order to do that, I wanted to point out where they are on the astroseismic HR diagram that Mai showed. So they're basically right on the main sequence. The main sequence pulsators with masses ranging from 3 to 9 solar masses. And from space-based observations, we found out that they're also multi-periodic gravito-inertial mode oscillators. And these gravito-inertial modes are of low degree, typically, and high radial order. And have periodicities of around 0.5 days to 5 days. The gravito-inertial modes are excited by the iron group capacity enhancement around 200,000 Kelvin in your radiative envelope. And so they drive the modes by means of the Kappa mechanism or the heat engine mechanism. A somewhat crude overview of the energy transport inside these slowly pulsating B stars is that we can talk about it as having a convective core in which our gravito-inertial modes do not propagate, and then we have a pretty extensive radiative envelope in which they do propagate, and of course there's overshooting going on all around the core. These slowly pulsating B stars also exhibit widely varying rotation rates, but I will show you a bit more about that later. So why is it important to talk about these slowly pulsating B stars? Well, I thought that I wanted to use this opportunity to talk about what has already been accomplished using linear astroseismology, but Mai already mentioned quite a bit of the results that I wanted to briefly talk about. So this counter-rotating star at Triana et al. is a very interesting result, and it gets me excited at least. And then, we have the wonderful simulations that were done by Mai and their team on internal mixing, but then we also have some mode excitation, recent work on mode excitation, and also recent work, relatively recent work on deciphering the internal magnetic field strength using a specific model by Basjaft et al. In 2018 for one single SPB star. Now, this is all within the realms of linear astroseismology, where we only use the frequencies to probe these, internal mixing and internal rotation, internal magnetic fields. What I would like to talk to you about today is actually entering the realms of nonlinear astroseismology. And if we do that, we can also try to account for the amplitude limitation. So basically how the modes that we are probing with our space data attain the specific amplitudes that we view them at. And what I also find interesting is what the difference would be between the frequencies of these modes in a linear framework compared to the nonlinear framework. So in order to do that, in order to enter these realms of nonlinear astroseismology, we use a sample of 38 Kepler SPB stars, and 26 of them are shown on this astroseismic HR diagram made by Mai in 2020, where you where you can see that this sample actually probes the entire mass range that I was talking about. It's like from 3 solar masses all the way up to 8 solar masses. And there's also an indication of how many of these stars we think are binaries, which is not a lot. We only have, clues, about 3 of them being binaries. And what is also shown in this in the color plot on the screen is how many of these modes, how many of the dipolar and quadrupolar modes are thought to be excited according to current non-adiabatic linear astroseismic theory. As I told you, these stars rotate at varying rates. And for our sample, again, I show you the results for the 26 SPB stars for which I determined the rotation rates. This is not that important at the moment, but what is important is that we look at the y-axis, where you can see that the rotation rate is going up, going from all the way from around 0% rotation, all the way up to around 100% critical rotation. And I must say this is the Roche critical rotation rate. And we see that our sample also approaches the entire rotation rate that we assume for SPB stars, rate range. So how do we go about probing the variability in these stars? Well, we use a tool, we use pre-whitening to do that. So these, what we do is very extract the light curves from the Kepler data, which we do in a so we make sure that we don't extract any artifacts. We make sure that there's not any contaminations inside these light curves, and then we subject that to Fourier analysis, and from that we obtain in our case a Luhn-Scarrow periodogram, and then do a signal selection. So we determine which of the signals in the Luhn-Scarrow periodogram is deemed to be well, not most important, but which one has the largest amplitude. It's a significance criterion, basically. And then we add that to our sum of science model, do a least squares regression, obtain the model, well, our sum of science model, and then subtract that from the light curve to obtain the light curve residuals. Fit that again to the Fourier analysis tool, signal selection, and we go about until we reach a certain point at which our significance criterion tells us that the next signal that we're trying to extract is not well, significant anymore. And then we end up with the light curve model that we can then use in our theoretical applications, in our model. So an example of such a Luhn-Scarrow periodogram, in fact, I'm showing you 2 Luhn-Scarrow periodograms in one, is the following, where this gray Luhn-Scarrow periodogram is the periodogram of the original light curve, and the orange one is the one we still retain of the residuals that we retain after pre-whitening. In the linear astroseismic approach, we tend to we don't use combination frequencies, and what we then tend to end up with is that we have we probe a lot of the pulsations in the main frequency group, so the one with the highest amplitude typically, and then the other pulsations are basically combinations of the ones in this group. What I wanted to show you here is that next to frequencies, we of course also have these amplitudes and phases in our model, which we in the linear astroseismic approach do not utilize at all. And in the nonlinear astroseismic approach, we should utilize. So in order to be self-consistent, you have to check, we perform this pre-whitening analysis in 5 different strategies. So we vary our strategy, we vary the way we determine the significance of our signal, and we vary the way we fit or perform the least squares regression. So you then end up with 5 light curve models, and of course these models need to be compared. And in order to do that, we compute a fraction of scaled variance or explained scaled variance. So this is basically the fraction of variance that you all know. These are the points from the light curve. This is your light curve model, and this is the mean light curve. And this is then a factor that accounts for the amount of points in your light curve and the amount of parameters in your model. If we subject our 5 pre-writing strategies for all 38 stars to this, if we compute that fraction of scaled variance for all 38 stars, we end up with the following graph. So we make a distinction between high FSV stars, which are stars for which our sum of size model seems to be very good at modeling the light curve. Whereas on the other side, the blue stars are low FSV stars where the model does not seem to work that well. For the high FSV stars, the pre-writing strategy does not seem to matter that much. The results are very similar in terms of the fraction of explained scaled variance. There is somewhat difference between different strategies for the low FSV stars. Now, of course, we want to talk about weakly nonlinear mode coupling. We want to talk about nonlinear mode coupling, but I'll limit myself to weakly nonlinear mode coupling. And we want to know what the observational characteristics are of these resonant three-wave coupling. So one of these is the frequency detuning. So this is the difference between the frequency of your daughter mode and the linear combination of your of the frequencies of your parent modes. And for the modes that we are considering, for the part of the parameter space that we're considering, this should be approximately 0 cycles per day, so that we have a frequency locking. And then for the resonant phases, we compute the same difference basically. So we have the phi of your phase of your daughter, and we subtract the linear combination of the phases of your parent as well. And this should be approximately some integer multiple of pi over 2, and that was inspired by theoretical expressions developed for non-rotating stars by Van Holsten and Beeck et al. In the 90s. So, like I said, the linear what we probe in linear seismology are these predominantly these signals in the main frequency group, and what we were trying to what we want to find out is whether these signals in these other groups could be the product of nonlinear mode coupling between these linear modes. If we look at these observational characteristics for nonlinear mode coupling through our entire sample, we find that the number of candidate resonances, so the number of resonances that fulfill these two equations that I showed earlier, is significantly different from 0. So we do find candidate resonances in most of the stars in our sample. In fact, we find it for 32 out of 38 stars that we consider. So one could say that resonant couplings seem to be ubiquitous in our slowly pulsating B stars, and one can say even more that these resonant phases that we observe are quite spread out in parameter space as well, from minus 2 pi to pi over 2. So these lines are supposed to represent the integer multiples of pi over 2. So what do we do now? We have these interesting quantities that we computed. So how can we utilize these quantities? So in order to answer that question, well, then we need to go back into the theory part. And I'll start off by describing how we usually describe gravito-inertial modes in linear astroseismology. And basically what we do is solve these linear equations of motion, where you have your driving term, you have your Coriolis force term, and you have your pressure and buoyancy force term. Within the assumption that the usual assumption that we then also make is that these are uniformly rotating inside, and that there's no centrifugal deformation taking place. even within these assumptions, we still have this Coriolis first term that renders the separation of variables impossible. So we need to do another thing. We need to make sure that, well, in order to obtain this equation of motion, we need to do another thing, and we need to, okay, thank you. We need to make the traditional approximation for rotation, in which we neglect the horizontal component of the angular frequency vector for rotation, which then renders it possible to separate the variables and obtain this nice equation above. Now, in the case of wave coupling, or in the case of weakly nonlinear asteroseismology, we can add another term on the right-hand side that corresponds to a nonlinear acceleration, and then we call these, well, then we obtain what we call the decoupled mode equations. Now, this is a very simplistic way of writing down this equation, but this consists of quite a few number of terms on the right-hand side. And one way of solving these coupled mode equations, it's a set of mode equations, is to expand this Lagrangian displacement vector in the linear eigenmodes that we computed from solving the linear problem for the different modes that we observe. And then we have these amplitude terms that start to pop up because of our expansion in linear eigenmodes. When you then add this, expansion into the decoupled mode equations, and you account for the orthogonality of these modes, which is modified because we're talking about modes in rotating stars, you then obtain the amplitude equations, which then finally we have an equation to work with. This is the equation that determines how your amplitudes would change over time for your gravito-inertial modes in these SPB stars. Now there are some extra terms popping up here. So we have the linear growth rate that determines the linear stability of these specific gravito-inertial modes. And we have these coupling coefficients that are a function of the linear eigenmodes themselves and the frequencies. Now these linear eigenmodes and linear frequencies we can obtain from the adiabatic linear solutions, and the linear growth rates we can obtain from non-adiabatic linear solutions. So this still, using this framework, we still don't have a direct way of comparing these the coupling coefficients to our observational characteristics that we determined before. And in order to obtain that, we then have to make an analogy to what was done in the 90s for the non-rotating case and look for the stationary solutions of these amplitude equations. And then we can finally start to use these frequency tunings and these relative phases to learn something more about the amplitude limitation. But that is still on the table for future work. So what I would say is a conclusion of our work, our recent work, is that we should really try to exploit more information from the observations. Not only look at the frequencies, but I think the amplitudes and phases are important also. And when we do that, we must make sure that we're using a self-consistent way to do that. And then we could look at doing multiple, doing the pre-widening multiple different ways, and constraining or constructing in an error budget. So what type of so how large the error actually is on your frequency due to the different pre-widening method that you're using. And finally, what is also very interesting is that the divergent couplings seem to be ubiquitous in our SPB gravito-inertial modes, at least within our sample. The prospects and outlook, at least for me, is to model these two-wave coupling, this two-wave coupling among gravito-inertial modes in slowly pulsating B stars, more specifically the stationary solutions of these amplitude equations that I talked about earlier. And what I would also find really interesting is the equivalent of nonlinear frequency shift for rotating stars within this nonlinear formalism. because, well, this has already been characterized back in the 80s for non-rotating stars. But what we now have to deal with is the Coriolis force for our rotating stars. And there was, I don't think that I've seen an analytical expression at the moment for describing this frequency shift. However, if there is a nonlinear frequency shift that we're not taking into account, this could also have an effect on our period spacing patterns, which we use to probe the internal rotation, the internal magnetic fields, the internal mixing. So I think this is a really important point that we need to try to solve. And I will leave it at that.
Okay, questions?
Hi, I'm Joel from Yale. Thank you for the excellent talk. I wanted to get your opinions on what you can do with this three-wave resonant coupling nonlinear stuff. So do you think you will be able to get nonlinear damping or growth rates to say something about the relative amplitudes of these nonlinear modes?
At least we can, I think we can do that for the stationary solutions. If the amplitudes are varying over time, that's a whole other thing. Then we need to try to numerically integrate these amplitude equations. These amplitude equations basically. And this, well, the thing is, this is already quite computationally intensive to compute these coupling coefficients. So I'm not sure how long it would take to numerically integrate these equations at the moment.
Thank you.
Hi, Adrian Fraser. This isn't my field, so I worry I'm going to ask a naive question. Sorry. So it is about this stuff. So I spoke to, I think Keaton Burns has done some work looking at sort of nonlinear mode coupling using a similar formalism here, and I think he did it with some of the people who were cited there. I think the impression I had was that sometimes you run into a problem where you need gobs of modes, and you need to know a lot about all those different modes in order to get the information that you want out of this formalism. Isn't that a problem here? I mean, you need to be able to use just a few modes to describe the state pretty well in order for this to be reliable. Isn't that right? That is correct, yeah. I mean, I know that there are, I think Nevin Weinberg also performed calculations for mode coupling in red giants using a similar formalism, not the same formalism. But then he used big networks to try to, well, determine the coupling for I'm not sure for how many modes, but maybe hundreds of modes. So yes, that is a potential problem. But then again, the observations point out that there seem to be these frequency locked frequencies that exist basically, and it would be, well, this is the formalism that we can use to at least to look at these three waves that are already coupling, and then we can go big basically.
Thank you. JJ Zanassi, research associate at CETA. So my question, I think, was similar to Joel's, but it's more observational. So the daughter modes only get excited when the parent mode has a sufficiently high amplitude. Are there any observational prospects of backing out what these amplitudes are observationally by looking at the flux variations in the light curve? Or
so I think you're talking about non-stationary solutions now, right? Or
I guess either stationary or non-stationary. I mean, just they have to pulsate, right?
Yeah. Okay. So these equations allow you to find also different types of stationary solutions where there's only one mode excited of your triplet, and the other one The other ones are basically, well, slave modes that are driving the other mode. So the observations point out that there are 3 modes that are excited, that have a measurable amplitude, in a sense. Well, not in a sense, they have a measurable amplitude. And these seem to have this specific resonant relationship. So now I'm forgetting what your question was.
I just want to be able to actually measure the amplitudes of the modes just by looking at how much the light curve is wiggling. That's it.
Oh, that's my computer, sorry. So that's basically what we're doing with the construction of our sum of science model, right? And these are the amplitudes that we're using. Well, these are the amplitudes that we're going to be using in our theoretical models. These are the phases that we can use to construct these resonant relative phases. And this is what we compute the frequency detunings with.
Question from Pascal Garot. When you write down your equation for the amplitudes, there's a linear term, a linear growth rate. Is that a growth rate? i.e., is it positive, or in this case it would be negative with this this sign? Is it a damping rate? If you have
depends on the sign of the term, right?
Yeah. What's the mechanism for the instability when there's actual growth?
Well, this is, you're just talking about the excitation mechanism. Oh, that's the kappa mechanism that I talked about all the way in the at the first slide, I think. The kappa is the typical heat engine mechanism that we find in these slowly pulsating B stars.
Hi, thanks for the very exciting work. Regarding the nonlinear coupling, oh sorry, I'm Bindesh Tripathi from UW-Madison. Regarding the nonlinear coupling coefficient, do you happen to have a sense of how big those are compared to the linear eigenfrequencies on the order of magnitude?
Not from the top of my head at the moment. Actually, no. I'm sorry, I don't know by heart how large these coupling coefficients are. This is also the part of the work that I'm still doing right now. So I hope to get back to you in a few weeks.
Hi, Vicky Antochi here. Thanks for the nice talk, and thanks for attacking this issue that's been bothering the community for decades. These combination frequencies exist in many types of stars, right? So I was wondering, I think it goes together with this excitation question here. How can you be sure that your daughter modes are actually excited by the kappa mechanism and not by resonant coupling? And also related to that, is it important to know which one are the parent modes and which are the daughter modes? Sorry if it's too complex.
No, yeah. So in order to well, let me go back to my observational part at least to, oh, I think I was putting my hand in front of the microphone. Is it better? Okay. So in order to compute these specific delta news and these relative phases, of course, it's important to know which one is the daughter and which one is the parent. What we did, what I did in this in our latest paper is compute these for all different combinations for all the different frequencies in our list. So and then look at the statistics of well, how many, well, basically what this plot shows, how many of these are actually fulfilling these equations. Does it matter from the theoretical side? Well, should, I think. But yeah, I mean.
So the reason I'm asking is because there is a paper, I don't know, some years ago by Don Kurtz and collaborators, showing that the assumption we made so far as a community that the highest amplitudes are necessarily the parent modes does not necessarily have to be true. So that was my
At the moment, we assume that assumption.
we can talk later.
Yeah.
Okay, so we are out of time for the session. So let's thank Jordan again.